Okay, so after talking this morning what we know about 4%, I see how we can approach the rest of the 96%. Okay, so I will talk to you about the future of particle physics. So clearly a large part of the future is machines at the energy frontier, where I will spend the largest time. And then, of course, there is a large program on neutrino physics going on, where I will say some words. And I will also say a little bit on the flavor sector. Okay, as an introduction, all regions have defined a strategy for the future of particle physics in the recent past. The American report from EPP 2010 has come out in spring. So this was a report to the American Academy of Science defining the strategy for particle physics in the next couple of decades. The European statement will be decided by the CERN Council next week, actually on July 14th. All regions come to very similar conclusions, although the European statement is not official yet. So let me read to you as an example the American one. So this is the priority list from the EPP 2010 report. So fully exploit the opportunities afforded by the construction of the Large Hadron Collider at the European Centre for Nuclear Research. Plan and initiate a comprehensive program to become the world-leading centre for research and development on the science and technology of a linear collider, and do what is necessary to mount a compelling bid to build the proposed international linear collider on US soil, and then expand the program in particle astrophysics, pursue an international coordinate stage program in neutrino physics. And in addition to that, in Asia and also in Europe, a super B factory, some progress in flavor physics is discussed. But I think the clear thing here is the LHC is the future of particle physics. That is already decided, and that is highest priority. But then still we should stay at the energy frontier, and with the next highest priority construct the international linear collider. Of course, the rest is important, but then with lower priority. Okay, so somehow following from my talk this morning, what are the fundamental questions of today's particle physics? So clearly, how is the electroweak symmetry broken? Is there a Higgs sector, or are masses generated in a different way? What is the matter from which our universe is made of? Can we see the dark matter around us in the cosmos and at colliders? Is there a common origin of forces? So do couplings or masses unify at some scale? Why is there a surplus of matter in the universe? So can we find the missing CP violation that we need for that? How can gravity be quantized? So are there superstrings, or are there extra space dimensions, or anything else that can point into this direction? And what does the neutrino sector look like? Which means, is there a new type of matter like Majorana fermions, or do the neutrinos contribute to baryogenesis, so to this CP violation area? What is the surplus in the matter made of? Okay, most questions are at least partially answered by colliders at the energy frontiers. So these experiments are actually the backbone of the particle physics program in all scenarios. However, especially the neutrino sector needs a special program on its own, and there is a wide range of proposed experiments, and all regions call for a well-coordinated effort. And I should have underlined here well-coordinated. There is absolutely no point in having a neutrino factory in the States and the same thing in Europe and the same thing in Japan. Our resources are so limited that we really should do all these things together. And there are a lot of complementary answers coming from non-accelerator and astroparticle experiments. For time reasons, I will not talk about this, but there is a diverse program going on within particle physics, but also somehow financed by nuclear physics, astronomy and space science. Okay, let me come now to the energy frontier. So to reach the highest possible energies, you collide high energy particles with high energy particles, not to lose energy in the boost as in a fixed target experiment. You know the root S of a collider is just twice root E, while the root S in a fixed target experiment is 2 times the energy times the mass of the target and the square root of that. So you build colliders to get to the energy frontier, and most colliders, at least in the past, were a storage ring, which had in this case you can reuse the beams many times. So there are mainly 2 kinds, which are hadron colliders like proton-proton or antiproton, and there are electron colliders like electron-positron. And there are a few special machines like electron-proton to study the proton structure, go to study quark-gluon plasma and things like that. So what is the main difference between these 2 types of colliders? Okay, first we have the hadron colliders, and the nice thing with the hadron collider is because of the high proton mass, actually you can reach very high energies. However, there are a couple of disadvantages. You know that protons are composite particles, so you shoot a soup of quarks and gluons against a soup of quarks and gluons, and so the parton energy is clearly much lower than the proton energy. The interaction at the parton level is unknown. If you have one event, you never know was it a UU bar or a DD bar or a blue or whatever. The proton remnants disappear in the beam pipe, so the kinematics of the event must be reconstructed from the decay products. Protons have strong interactions, so you get a high background, and not all processes can be reconstructed. So in this sense, hadron colliders are discovery machines. You reach the highest possible energies, but with quite a lot of disadvantages further on. Quite contrary to that are lepton colliders. Because of the small electron mass and the synchrotron radiation, it is much more difficult to reach high energies, but then electrons are point-like, so the interaction energy is equal to the plus and minus energy, and you can use energy momentum conservation to reconstruct the event kinematics. Electrons don't have strong interactions, so you have low backgrounds, and all events that are actually produced in your detector can be reconstructed. Okay, apart from neutrino, of course, but and in that sense, lepton colliders are then more the precision machines with which you can really do precision measurements. Okay, so let me come to the closest future. You heard already the last lecture about it, is the LHC. So this is not yet a photo, this is still a computer animation. The LHC is a PP collider in the lab tunnel at CERN. It has a center of mass energy of 14 TeV. It will start summer next year with luminosities up to 10 to the 34 per square centimeter and second. And as one feature, for example, you have 10 QCD events per bunch crossing. It's called pileup at the high luminosity, which shows you somehow the difficulties for experimenting at this machine. So there will be 2 multi-purpose experiments, which is Atlas and CMS. This thing is not to scale. Atlas is actually like a four-story building. You have an inner detector which looks pretty standard, but then you have this huge muon toroids around it. So if Atlas would be watertight, it would actually swim. And contrary to that, CMS is a very compact detector with a much larger magnetic field. And in addition to this multi-purpose experiments, you have one V-physics experiment, LHCb, and a heavy ion experiment, ALICE, where we heard a little bit about yesterday. So what will be the physics at the LHC? The first priority clearly is to find the origin of electroweak symmetry breaking, which probably may be the Higgs. However, the discovery reach extends much beyond that, for example in supersymmetry, but also in other cases. The typical mass reach goes up to something like 3 TeV. Strongly interacting particles have a huge cross-section, but also weakly interacting particles are visible if the decay signature is clean enough, for example if they decay into leptons. Let me show you 2 examples from physics at LHC, and let me start with the Higgs. So this is the Higgs production cross-section, and you see it's pretty large. It goes into the 10 picobar region, but the largest process is glue to Higgs, which you see here. But then you have also this so-called fusion process, QQ goes to Higgs QQ, where a W or a Z pair fuses into a Higgs, and also some other channels that play not such an important role. However, especially if the Higgs is light, the dominant process is blue to Higgs to BB bar, but this is absolutely hopeless to see because it is completely hidden in the BB bar background. So the discovery channels are Higgs to gamma gamma or Higgs to ZZ for electrons, while Higgs to BB bar or Higgs to tau tau may be seen in association with W or Z. So in this type of diagrams where you have something else in the detector that you can use to tag the Higgs, and then you are no longer so sensitive background in Higgs reconstruction. So that is what Higgs signals at the LHC can look like. If the Higgs is rather light, you can see it in Higgs to gamma gamma, and this is already a zero suppressed plot. So zero would be somewhere here in the bottom, on the bottom, and this is a QCD cross section, and you just see a little bump that is coming from the Higgs. Nevertheless, when you understand the background and abstract it, you see here that you are able to extract a statistically significant signal. It's much easier if the Higgs is a little bit heavier and it can decay into ZZ, into 4 electron, where you see here the Higgs peak basically without any background. And this actually happens already when the Higgs is much lighter than the ZZ, because one of the two Zs can be off shell. So you see the Higgs discovery range. You see the Higgs discovery range here, and you see, okay, here in yellow is the exclusion from lab, so you don't have to care what is left of it. Then there is only a small part left for which you need the gamma gamma channel, and then already the ZZ channel sets in, and only in the region where the two Zs are not yet on shell, but the Ws are already on shell, the ZZ loses significance, so you need the WW in addition. But then again, you can do basically everything with the ZZ to 4 electrons. And the important thing is the LHC can discover a standard model Higgs over the full mass range. Let me, as a second example, show you briefly supersymmetry. So quarks and gluinos, so the partners of the quarks and the gluons, have strong interaction to collide protons. So you start with colliding strongly interacting particles. So you have huge production processes, cross sections. On the contrary, the gauginos and leptons, so the partners of the leptons, the W, the Z, the Higgs, and so on, they can be produced in cascade decays. When these particles decay, they don't decay at once. They decay over many steps, and you produce the other particles here. Like a typical chain could be a quark goes to a quark and a neutralino 2, and the neutralino 2 goes to a quark, a lepton, and a slepton, and then a slepton goes again to a lepton and a neutralino 1, or even longer. So you can reconstruct these particles in decays. Of course, details of the cascades depend strongly on the SUSY parameters, so that is something that is difficult to predict in a very general way. And if the mass differences are too small, also particles can be missed. For example, if these two particles, like the lepton and the neutralino, are very close together, this lepton gets only very little energy, and so it is not reconstructed. So if the mass difference gets small, there is quite a chance that you miss some of the particles. If this so-called R parity is conserved, this means if the lighter supersymmetric particle is stable, so then I'll come to it later, it would also be a nice dark matter candidate. But if this is stable, so it is invisible in the detector, so SUSY events have a large missing momentum, and this ensures a fast discovery of SUSY and a crude measurement of the mass scale. And this is shown here, where here is shown the effective mass, which is a mass that is built out of the visible jets and the missing transverse energy. And you see that you get a huge enhancement at large effective mass over the standard model background. And this plot shows the correlation between the average effective mass that you see and the mass scale of SUSY, and you see there is a nice correlation. So you get already from this sort of plots a good estimate of the mass scale of SUSY if you discover it that way. But you can also do much better. You can measure particle masses. Actually, if the lightest particle is stable, there are no mass peaks because this particle is always lost, so you can never reconstruct supersymmetric particles. However, you can still measure mass differences by measuring kinematic endpoints. For example, if you have a Chi02 decaying into a lepton and a lepton, and this decaying into a lepton, and Chi01, the mass of this pair plus the mass of the Chi01, of course, has to be smaller than the mass of the Chi02, because otherwise the kinematic doesn't work anymore. So if you plot the two lepton mass, you get a sharp edge at the mass difference. So this mass difference actually can be measured very accurately, while the LSP mass is very difficult to measure in a model-independent way. So far to the physics of the LHC. Is there a future of the LHC after it has run in this standard mode for 6, 7, 8 years, whatever it will take? Yes, there is. There are possibilities for upgrade. People are already discussing a luminosity upgrade, and up to a factor 10 seems possible, taking three measures. You can increase the bunch charge by a factor 1.5. You can increase the number of bunches by a factor 2, or you can reduce the focusing of the beam, so make the beam smaller and increase the luminosity by that, by increasing beta star by a factor of 2 or a little bit more. And from the machine point of view, all this seems to be not an enormous problem, so the machine guys are confident that this is possible. However, I've shown you there are already 10 pile-up events at high luminosity. So if you increase by a factor 10, you have 100 pile-up events, or 50 because if your detector is fast enough, because the factor 2 you get here from the bunch number. But then if you increase the bunch number, your electronics even has to be faster to separate the bunches. So a significant detector R&D is needed to cope with the higher background and the shorter bunch time. So experimentally this will be extremely challenging. Much more interesting would be an energy upgrade. So a factor 2 is desirable, but the LHC dipoles already now have to run at 8.5 Tesla, so you would need 17 Tesla dipoles. And for this, a huge R&D effort is needed, and probably you cannot do it anymore with pure niobium, but you have to go to this niobium-3 tin superconductors. So this is from the magnet R&D a huge challenge, and it's by far not certain if this will be ever possible. Let me come now to the plus and minus side, so the plus and minus linear collider. I told you already, synchrotron radiation in circular machines is very hard. It goes with e to the m to the 4th power divided by the radius, or to the 1st power. And for example, at 200 GeV had a circumference of 27 kilometers, and delta E, so the synchrotron radiation loss per turn was 2.5 GeV. So if you want to increase this now by a factor of 5 and want to stay with the radius roughly in this area, you would have a factor 5 to the 4 more energy loss. So you lose much more than the beam energy in one turn. So this simply becomes completely impossible. So the only way out now is to go to a linear collider instead. So you have two linacs, you shoot the linacs at each other, and you have a collision point in the middle. So the problem here is you can use each bunch only once, because you accelerate it, you collide, and then you dump it. So this, of course, is a huge luminosity loss. But future collider needs a higher and not a lower luminosity than what we have up to now. So you have to compensate by extreme focusing, and people are discussing about bunch sizes of something like 5 times 100 nanometers, so really tiny bunches. And the main challenges here are you need high accelerating gradients to keep the machine reasonably short, and you have to have an extreme beam steering to achieve this small beam size. And not only to achieve this small beam size, in a circular machine, basically the two bunches run per construction on the same orbit, so it's kind of easy to get them collide. But now you have two arms that are completely independent of each other, and nevertheless the two bunches have to be at the same place with a precision of 5 nanometer in the vertical scale. So the ILC is actually now a sort of real project, so that is something that may become real reasonably soon. So the ILC is a linear collider based on superconducting technology. The ILC is an international project that is supported by all regions, and the technical design actually is currently underway. So what are the gross parameters of this project? In the first phase, the center of mass energy should be able to go up to 500 GeV with an upgrade possibility up to 1 GeV. For this you need a tunnel length in the order of 30 kilometers, so it's basically the same length as LHC, just stretched, so there is not, from the tunnel length it's something completely reasonable. The accelerating gradient is thought to be in the order of 35 MeV per meter, and the luminosity should be in the order of 2 to 5 times 10 to the 34, so this could give you 200 to 500 inverse femtobarn per year. And also you could do a little bit more with this machine than just doing plus and minus collisions. Of course you can, now the two arms are independent, so you can fill both arms with electrons instead of positrons, so you can have E minus collider, or in a few millimeters before the IP you can collide the electrons with a high power laser and thus convert the electron beam into a photon beam, and then the photons basically follow the path of the electron, so you get also this nicely focused photon bunches, so you can run the thing as a gamma-gamma or a E-gamma collider, or you can run the thing back at the Z, as in the so-called bigger Z option, where in a couple of months you could get a billion Zs and redo all the physics that we have done at lab with much better precision. Okay, so that is the basic layout of a linear collider. Of course, you have what you need. You need a source for the electrons, for the positrons. You need damping rings. Then you have the main section, which is the LINAC, and then you need some final focus system, and you have 1 or 2 detectors in the center. And this main LINAC sections now have a length of roughly 10 kilometers each, and they consist of this basic structure, which are in the ILC case 9-cell niobium cavities. And this is the time schedule in which we could get a linear collider. So we are presently here in the reference design phase. So this reference design currently is underway. It will be finished by the end of this year, followed by a very detailed technical design in the next 2 years. Then somewhere in 2010 you will start to get physics results from the LHC, which then hopefully is enough motivation for the politicians to approve this project, and so then you need another 6 to 7 years to build it. So if we have semi-intelligent politicians approving the thing here, we could have 2016, 2017 get first collisions. Okay, let me show you a few highlights of ILC physics. First, there is the top quark. The top quark, we know it's there, so it's no speculation at all. And in direct reconstruction, like at the LHC, if you reconstruct an object in the detector, the object that you reconstruct always is color neutral, but the top is colored object, so you never can really reconstruct the top in the detector. You always have, you reconstruct the top plus something or the top minus something, and this leads to an intrinsic uncertainty in the order of 1 GeV on the top quark mass, which cannot be overcome. This problem does not exist, for example, in the plus and minus threshold scan. So the ILC actually is able to measure the top mass and width with an error of smaller than 100 MeV. And you see, for example, here how well the top threshold is understood by now theoretically, and this is a next to leading log calculation by Wang et al., where you see that you really understand the position of the threshold. So this 100 MeV is something reasonable. And this good top mass measurement is actually something important. You have seen this morning the top mass enters the electroweak electroweak fix, the Higgs prediction, and so on. So there it is pretty important, and it's even essential if you want to interpret the Higgs masses within supersymmetry, where the radiative corrections from the top are huge, and there is absolutely no reason to measure the Higgs mass to 50 MeV when you know the top mass to 1 GeV. So you really need this precision to progress there. Another important point for the ILC is Higgs physics. So the Higgs sector is experimentally only very poorly known, and the discovery of a Higgs-like particle does by no means fix the Higgs sector. In the standard model, of course, it does, but there are lots of extensions which would give you a different sort of Higgs sector. So so you should not just measure the Higgs, see a Higgs particle, but to understand electrode symmetry breaking, it is necessary to measure couplings of the Higgs system in a completely model-independent way. And for example, one nice thing the ILC can do is you can measure the HZZ coupling in a completely model-independent way by using a recoil mass technique. I said already, you can use the kinematic. Because you have the full event in the detector, you can use for momentum conservation to reconstruct your events. And for example, if you have a plus and minus goes to a Z, the Z then goes to a Z and a Higgs, and the Z decays into 2 muons. So basically, you just reconstruct the 2 muons. You don't care at all what the Higgs is doing. You just reconstruct the 2 muons. You calculate from energy momentum conservation the recoil mass against these 2 muons, and you get this nice peak. So this is the background, and this is the Higgs. So you see, you can measure the Higgs mass, and especially you can measure the Higgs production cross-section, which is proportional to the HZZ coupling in a completely model-independent way, not caring at all how the Higgs is decaying. So you get this coupling in a model-independent way, and also you get here a completely unbiased sample to do absolute branching ratio measurements. Then in addition, you can measure the Higgs self-coupling on something like a 10% level using E plus and minus to ZHH or E plus and minus to nu bar HH, which also gives you now access to the shape of the Higgs potential itself. And when you put all the coupling measurements together, you can really prove that the Higgs couples to mass. So this is the prediction, and the central values, of course, are still guesses, but the error bars are estimates what you can do at the ILC, and you see that you can really measure the couplings of many particles with very good precision. And if you now go a little bit model dependent to see what you can do with these measurements, this shows for a couple of examples what you could do with this precise measurement. For example, if you have a 2 Higgs doublet model where you have not 1 Higgs but you have 2 Higgses and they couple in a somewhat different way to the up and down sector, you would see that your uptight particles are shifted against the downtight particle with a very you could see this with a very good sensitivity. Some models of baryogenesis need stronger Higgs self-couplings, and these are effects that you could see. Or if you have some extra dimension models where the Higgs mixes with the radion, so with one of these particles that is generated by the extra dimensions, all the couplings would be down by some amount, and also you could see this. And because to measure the partial width or the branching ratios of so many particles, you could actually distinguish the different types of models. Let me also, for the ILC, talk a little bit about supersymmetry. The LHC clearly mainly can see strongly interacting superpartners like squarks and gluinos, and the others may be seen in cascade. On the opposite, for the ILC, the squarks and gluinos are probably too heavy, so they will not be seen, but there is a very high chance that one can do precision measurements of leptons, charginos, and neutralinos. The LHC can measure mass differences pretty accurately, while it has problems to measure the LSB mass. On the contrary, the ILC can measure all masses and couplings, even the LSB, of all particles that are in the accessible range. So SUSY is clearly a very good example how these two machines are complementary and can help each other. So this is a study that has been done in the so-called bulk region, where the supersymmetric masses are relatively light. So both machines can see a rich can see a rich spectrum, and there you can really compare what the two machines can do and how they can help each other. So this I said already, but the important point is here, I showed you this one plot. The LHC measures mass difference pretty accurately, but has difficulties to get the LSP mass. And if you look here only at the black cloud, this is what the LHC would measure in the plane of the lightest neutralino mass versus the squark mass, and you see you get a huge correlation, and because of this huge correlation, your error on the squark mass is extremely large. However, the ILC measures all accessible particles very accurately, including the LSP, and this is as an example where you, for example, where you look at A plus E minus goes to smyons, and then the smyon decays into a muon and LSP, and then you just look at the energy spectrum of this decay muon, and this is basically a square distribution where the two endpoints are given by the smyon mass and by the LSP mass. So this LSP, the particle that you never see, you nevertheless get an extremely good mass measurement. And now if you go back to this plot, this blue band here is the precision with which you measure the LSP mass, and it's not extremely interesting on its own, but also if you impose that now on the LHC measurement, suddenly the LHC measurement, the LHC also gives you a very good measurement of the squark mass with the help from the neutralino mass from ILC. So this is a very detailed study what can be done if you take LHC, ILC and the combination. And let me just point out two things. There are some places where the ILC measurement is extremely accurate, but there are also lots of places where the combination of the two really gives you big advantages. And there are even places where the combination is much more accurate than ILC alone. And what can you do with that? For example, you can reconstruct all SUSY breaking parameters with typically sub% precision, and you can and with this you then can test grand unification. This is the coupling plot I've shown you already this morning, but just magnifying the high energy region, and the outer lines is where we are now. The filled inner lines is where we can go with ILC, assuming that the central values stay the same. But then you can do the same thing also for masses. For example, you can. This is the unification of the gaugino masses. This is unification of the fermion masses, and you can test unification also now for the different sectors of supersymmetric masses, and really understand grand unification if it exists in nature. Let me also say here a few words on high energy colliders and cosmology. 1/4 of the universe consists of dark matter, and the density is actually measured with very good precision from the cosmic microwave background. From galaxy formation, a mass around 100 GeV is favored, and to get the right annihilation rate, the dark matter particle should be weakly interacting. Because this is important, because you briefly after the Big Bang, you produce these dark matter particles in large amounts. They are just in thermal equilibrium, but then you have to get rid of them, but not all of them, just the right amount. So if they would, for example, interact strongly, you annihilate too much, so no dark matter is left. If they annihilate too weakly, then too many survive, and so there would be too much. So our universe would be closed and would have probably have collapsed already. So the cross section for these particles is very well fixed, and it has to be just in the range of a weakly interacting particle that it works. And so you see 100 GeV, weakly interacting particles. So this particle should be produced at the next generation of colliders. And supersymmetry actually predicts nicely such a dark matter particle, a lighter supersymmetric particle. Of course, other theories do as well. I just stay with supersymmetry as one example. However, within these minimal theories, the most probable solution actually are difficult for the LHC, because the most probable solution are exactly the solution where the mass difference between this lepton and the neutralino gets very small, so the LHC actually has a chance to miss that. So The task of the LHC and ILC clearly is to measure the mass of this particle, but also to measure all the properties of this particle, that you can calculate the annihilation rates, and then standard cosmology can calculate the dark matter density just starting from the Big Bang and evolving the particles up to a couple of milliseconds at most. And if we understand cosmology and particle physics, the calculated rate has to be equal to the measured one. And even in the difficult regions, the ILC can actually match the precision from the microwave background, which is shown here for one example, where the red line is what we know now from the WMAP satellite on the dark matter density. The yellow line is where we will go in a couple of years with the Planck satellite, and then you see here in this orange color what the LHC can do, and in blue what the linear collider can do. And so if the bandwidth and the linear collider actually coincide, you think that you probably have understand cosmology and particle physics, so you know the particles. You have a given amount of particles. If you calculate the density of these particles, you come to the universe that we have. So you get a feeling that things are understood. However, if these are if then the yellow band and the blue square will not overlap, you know that you are either missing something or something is wrong in cosmology and so on. So this is probably one of the most important tests you can do if you understand the particle physics and cosmology at the same time. So is there a way of lepton colliders beyond the ILC? Of course there is. However, the ILC technology gets too expensive beyond 1 TeV, because now at 1 TeV you are at 30 kilometers or a little bit longer. So if you want to go to 3-4 TeV or so, the collider will just become much too long. There are two possible ways out. Either you can think of muon colliders. A muon is much heavier than an electron, so a muon doesn't have the problem of synchrotron radiation, so you can go back to circular machines. However, it's very difficult to produce and cool muons in their short lifetime. For electrons, you can just you have time, you can do things in hours, but a muon decays in a microsecond, so you have to produce it, capture it, cool it, accelerate it, and then even still have some time that the bunches can collide at least a couple of times, that you can do physics with it. And this turns out to be extremely difficult, but it may follow from the R&D that is done for neutrino factories anyway. And I find at least extremely funny thing is, you know neutrinos as particles that don't interact, but you know also that the neutrino cross-section rises with rising energy. And once you are above 1 TeV, actually the radiation from the produced neutrinos may be a problem for a muon collider. So just because it's still, the neutrinos still interact weak enough that you cannot shield them, but they interact strong enough that they get dangerous. So there may be a serious problem with muon colliders. Another possibility is to stay with a plus E minus linear collider, but go to new acceleration technologies. There is first this two-beam scheme, which is the pursuit in detail in CLIC. I come to it on my next slide. But there is also even more ambitious schemes like plasma acceleration. And people actually have achieved in a plasma an acceleration in the order of 10 to 100 GeV per meter, which is a factor 1,000 larger than what we have for the ILC, which is great. However, the only problem is that up to now this is only achieved in short structures of a few millimeter, and also the problem for how to make longer structures or how to couple structures that you can accelerate a particle in different structures in a row is unsolved. So this is far away from being used. So closer to use is this CLIC project. The idea here is you have two-beam acceleration. So first you produce with standard technology a very high current, low energy drive beam. And this drive beam you guide through a structure of of high-frequency cavities, and then it's not in the usual way that you power the cavity from outside to accelerate the beam, but just vice versa. The beam goes through an unpowered cavity and then excites oscillation in this cavity, so the beam dumps its energy in the cavity, and then with some waveguides you transfer the energy that is dumped into this cavity into a parallel cavity structure, and then in this parallel cavity structure you accelerate the high energy beam that you want to use for physics. With this sort of technology, 150 MeV per meter can be reached, so this is 4 times the ILC. So in the ILC length you could do a 40 eV collider, and this is currently an R&D project which is pursued at CERN, and a proof of principle, if this scheme really works, should be available by 2010. So here I want to leave the energy frontier and come to neutrino physics. And most of it I have stolen from a talk of Cervera from this Orsay Symposium on the future of particle physics in Europe. So the present information on neutrino physics comes entirely from non-accelerator experiments, solar experiments, atmospheric experiments, reactor experiments. However, to progress further, controllable beams from accelerators are needed. The oscillation frequencies are still rather slow, so to get high oscillation probabilities you need long baselines, and we are talking here about baselines in the order of 500 kilometers or so. So this means you have somewhere an accelerator, and 500 kilometers away you have your detector. Of course you lose intensity somewhere with sort of 1 over R square loss. So you need very intense beams, and you need huge detectors to do this. And for the future, people envisage something like 3 steps. First, a sort of consolidation area where you confirm the parameters and show that really nu mu oscillates into nu tau. Up to now, we only know that the muon neutrinos are lost. We don't know for sure that tau neutrinos appear, although this is very probable. The next step is what is here called theta 1,3 area, which is to I've shown you the neutrino mixing matrix this morning, and you have seen the mixing between the first and the second neutrino is very large. The mixing between the second and the third neutrino is very large. But then, for some reason that nobody understands, the mixing between the first and the third neutrino seems to be very small. And up to now, this mixing angle, theta 1,3, one has only limits in the order of 10 degrees, but nobody knows its exact value, and quite a significant program will be needed to measure this angle. And then the hope is that this, in the end, can be followed by a CP area where you do precision measurements of the mixing angle, but then also access CP violation and try to see if there is really CP violation in the neutrino sector, which in principle should be there. So let me talk first about this consolidation era, so that is what is going on basically now. So people use conventional beams for that. So conventional beams means you just you take a proton beam, you shoot the proton beam on a light target, so you get all sorts of hadrons out, mainly pions. The pions decay into neutrinos in a decay tunnel, and these neutrinos are then, of course, mainly muon neutrinos, and this is a neutrino beam that you use. That is the way that all neutrino beams have been done in the past. There are 2 projects going on. There is a beam going from Fermilab to Minos, so that is from Fermilab in Illinois to Minos, which is in the north of, it's a mine in the north of Minnesota, and that is 730 kilometers. And this beam, this is a relatively low energy beam, so you get good statistics, so you can improve quite a bit on the theta 2,3 measurement. And slightly complementary to that is the CERN Granzasso experiment, where you start from the SPS and CERN, and you shoot a beam to Granzasso near Rome, which is basically the same distance, but this beam has a much higher energy, which means you get less statistics, you can't do such a precise measurement, but since you are at higher energy, you are well above tau production threshold, so you can actually see that taus appear and really prove that the muon neutrinos oscillate into tau neutrinos and not into something else. And both experiments can improve the theta 1,3 limit from the roughly 10 degree that we have now to 7 degrees. The next area then is an area where you really try to measure theta 1,3. The theta 1,3 is interesting in itself as a fundamental parameter, but also CP violation is only possible if theta 1,3 is not equal to 0. If you remember for the quark sector, this Wolfenstein parametrization, which I've shown you this morning, this complex phase was just at the two outer corners. So this would just multiply theta 1,3. So if you set theta 1,3 to 0, the complex phase is multiplied by 0, so no CP violation is possible anymore. And then I'll show you later the best strategy to measure CP violation depends on theta 1,3. So actually, also for this reason, this has to become before you try to measure CP violation. So the planned experiments here, there is the so-called T2K, which is under construction. These are super beams in Japan, whereas with super beams in the jargon means just take the conventional technology, but start with very high proton currents to get very intense beams. And this also allows you, I've showed you this morning, the mass hierarchy is not yet completely known. So if this more tau-like neutrino is the lightest one, or if the more electron-like neutrino is the lightest one, which is something which is still, both is possible, although probably we all think, why should it not be the same as in the other sectors, but we simply don't know. But since but these beams fly also a couple of 100 kilometers from Tsukuba to Kamiokande, but of course they don't fly through vacuum, they fly through the Earth, so you get matter effects, and again these matter effects can disentangle the two solutions, so from the matter effects you would actually get also the mass hierarchy. Another project going on here is called Double Show, which is a reactor experiment in France, which is almost approved. So here you have a very powerful nuclear reactor, but of course also with the reactor you are somewhat limited by the knowledge of the neutrino flux, and you solve this problem by having now two identical detectors at different distance from the reactor. So basically you can use the first detector to measure the flux, and then the second detector to measure the oscillation. And then there is this so-called NOVA experiment, which is in planning, an off-axis experiment at Fermilab. This off-axis technology also is a pretty interesting technology. Normally, of course, you want to go in the center. You want to go in the center of your beam, because in the center of your beam you have your highest flux. But now, if you go from the center of your beam slightly away, somewhere off axis, you can just show it from pure kinematics that of course the flux gets smaller, but the energy gets much sharper. Basically, the low energies are spread all over the place, while the high energy part is more going central. So this means if you go off axis, you have a beam of much better defined energy, although lower energy, but it is not a problem, but much better defined energy. And now if you want to measure oscillations, it's always good to, since basically you measure a gamma factor, m over e or e over m, you want to have this factor as constant as possible to get a constant in this sign. So this gives you much better. This can give you much better results. So this is a possible future of theta 1,3. So this is the world limit that we have now, and that is how the world limit can improve in future. Okay, this is with Minos and Opera, so with this with the Fermilab and CERN program. Here you would go with double shows, then you go here with the Japanese program, and even improve with this NOVA program at Fermilab. And in 10 years, and actually you see that you can get a little bit more than an order of magnitude, or almost 2 orders of magnitude in 10 years from now as a limit or a measurement on the way wherever the value turns out to be. So after that you can go to the CP error. Of course, the interesting observable here is you want to measure CP violations, so you want to show that the neutrino is different from the antineutrino, so you measure the symmetry of the electron neutrino oscillating into a muon neutrino minus the anti-electron neutrino oscillating in anti-muon neutrino divided by the sum, and this is basically the CP phase times a function of theta 1,3. But then you find out that you get additional ambiguities. First, due to theta 1,3 and its sign. For example, you see here the CP asymmetry. If you fix this delta as a function of theta 1,3, and you see it depends strongly on the value, and the error is almost constant. And you see here that for low values you simply cannot measure it anymore. But even if you measure this asymmetry alone, it really doesn't help you. For example, this is the symmetry that you measure as a function of the baseline for the two different solutions of the mass hierarchy, and you see they are, especially at larger baseline, they are vastly different. So you can do only a good measurement of CP violation if you have measured all these other parameters like this sign ambiguities, theta 1,3, and so on before. So what are people thinking about here? So the study technologies are first this, just take this super beam technology, improve it even more, and then go to really huge detectors. People are, at the moment we have something like a kiloton detector, so detectors with an active mass of something like 1,000 tons. And here you have to go now to megaton detectors to live with the standard technology. So it's all known technology, but getting very large. However, there are interesting other ideas. There is the idea to use beta beam, because in principle the cleanest source of neutrinos that you can have is a beta decay of a nucleus, because a beta decay of a nucleus just gives you an electron neutrino for a beta plus decay, or an anti-electron neutrino for a beta minus decay, and nothing else. So you really know exactly without any uncertainty the composition of your beam. So in a sense this is extremely nice. And there are some possible decays like the helium-6 decay into lithium-3 or the neon-10 into fluoron-10, which have a relatively short lifetime. So you can think of a facility where you produce, again shooting protons on a nuclear target, producing these nuclei, then capturing them, damping them, accelerating them, and putting them into a decay ring. So there is a hope that you can produce these beams. However, it's clear that that efficient generation of these nuclei, so to produce enough nuclei to get a high intensity beam, is extremely difficult, and R&D on that is ongoing. And you need clearly you need high energies to get a sensitive measurement. So you have to accelerate your nuclei very high. But then, of course, if you start with high energy neutrinos, again you need long baselines to get the oscillation. So the most ambitious idea that people have at the moment is use the LHC to accelerate these nuclei, and then build a detector at the Canary Island to get the baseline that you need. Probably interesting to work there. But then the last idea is the neutrino factory. So neutrino factory actually is a jargon for using muons, and let the muons decay to give you the neutrinos. So the concept is to produce muons and let them decay in a storage rings. So, and a muon decays, either a mu minus decays into a muon neutrino and an electron antineutrino, or a mu plus would decay into a muon antineutrino and an electron neutrino. But since you want to see oscillation between these two kinds, you see immediately that you need a detector with charge taking. Because if your detector can take the charge, you know if your electron neutrino that you see comes from an oscillation or comes directly from the decay. But with charge taking, you have no ambiguities left anymore. So you produce the muons in the usual way. You pion production via a proton beam with the pi to mu decay in flight. But the problem then is you have to cool the muons. And again, here also a large R&D program is going on, and the feasibility that this is possible at all is not proven. The detector, the complex then would look something like that. As usual, you start with a proton linac, then you with an accumulator ring and so on. You have a target. You have capture sections where you capture them and cool them, and then some accelerating sections, and then you put them into a ring. But okay, the ring clearly is not a ring anymore, because what you really want is straight sections, because all the muons that decay within a straight section are basically going along one beam line. And now it's just your fantasy how to arrange the detector. For example, with this triangle, you would get 3 usable beams, one over here, one over here, and the third one is not drawn, one over here, but there are of course other possibilities thinkable. The important thing, as I mentioned that already, the optimal technology to measure CP violation depends on theta 1,3 and on the other ambiguities. I've taken here a plot that chooses just one of the ambiguities, but then shows the reach in the theta 1,3 CP violation parameter area, and you see the curves cross. Then the curves are for different technologies, and you see that these curves cross. So this means if you turn out to be here in theta 1,3, you would choose the blue technology, which actually is the neutrino factory. While if theta 1,3 is very large, you would choose the black technology, which is a super beam, which are just super beams where you get more neutrinos but with less systematic knowledge. So this means actually you should wait with choosing your CP violation experiment until theta 1,3 is known, and just do R&D in all possible directions, and then do a well-coordinated effort on CP violation once you know theta 1,3. Okay, there are some additional neutrino measurements. Apart from the mixing sector, 2 questions remain. What is the absolute mass scale, and is the neutrino a Dirac or a Majorana? So the mass scale to the maximum electron energy and the shape of the endpoint in nuclear beta decays depends on the neutrino mass. This can be used in precise neutrino mass measurements. And if the neutrinos are Dirac particles, this is the only way to measure the mass scale. The current limit is in the order of 2 eV, but in future there is a plan to improve this to something like 100 MeV. There is the Katrin experiment in Karlsruhe, which is supposed to start in 2008. The other question is what I also discussed this morning: is it Majorana or Dirac? Also here we have a current limit in the 0.1 eV region at the moment, and there is also a diverse program going on which aims at the 0.01 eV region later. Okay, at the end let me briefly discuss the future of flavor physics. Why is this still interesting? We have no idea why there are 3 families in nature. We have no idea why the mixing is as it is. We have no idea why the masses are as they are, and we also don't know where the CP violation that is needed for baryogenesis comes from. Okay, neutrino physics clearly is flavor physics, but this covers 1/4 of the flavor sector. The rest has to be done with fixed target experiments for rare K or mu decays, low energy colliders for E, D, tau physics, and also high energy machines for the top, and also for the physics. So what is the present flavor program? So we have an active B-physics program at the Tevatron in 2009. I've shown you this morning, they just recently discovered BS oscillations, so really important things are coming out of this program. And we have two asymmetric B+/B factories at SLAC and KEK, also until 2009 with luminosities in the order 10⁻34. We have a program on charm physics, where the beam machines, of course the B always decays via a charm, so a beam machine naturally also does charm physics. And we have this special machine at Cornell, where the Caesar storage ring has been converted to a charm factory. And so we have a program of some other items, like at PSI in Switzerland, there is a progress for rare mu decays, which aims for mu to E gamma up to a limit of 10⁻13, and the B factories have also a significant potential on tau physics. So what is a possible future flavor program? In B physics, unitarity triangles and radicays are still statistics limited, and so there is a reason to go on here, and there are many observables that need hadronic modes, so they are difficult to be done with hadron machines, because with hadron machines the background usually is so large, you get the leptonic modes very nicely, but for the hadronic mode it will be hard. Okay, nevertheless, there is NHCB, the B-physics experiment at NHC, which is under construction, but there are ideas about the ± super B factories, which is all in the planning state. There is the super B program at KEK, which is a conventional B factory with 10 times higher luminosity, so you get to something like 10⁻35. But there is also these ideas on the so-called linear super B factory. Linear means because in the first ideas they were thinking just to use ILC technology using linear colliders to get run it on the epsilon and do B physics with that. But these programs have evolved, and what actually is left from the linear is that you use the damping ring designs from the linear collider. So you basically use the damping rings from the linear collider and put an interaction region inside. And but with these designs, you are able to get very, very small beams, and so get luminosities in the order of 10⁻36 with reasonable power consumption. And this should also be able to run in the tau charm or in the phi region. And Frascati is interested in this program if they can find international help in building and especially financing. There is also something going on in the K sector. There are some rare K decays, like K plus to pi plus nu nu, or K0 to pi 0 nu nu, that give theoretically very clean measurements on the unitarity triangle. You see here what you could do with K long to pi 0 nu nu, or K plus to pi plus nu nu, but you can imagine that especially such a decay is extremely difficult to observe, because you have K0 with a very long lifetime, and then you have somewhere the pi 0 in the detector and nothing else. At present, there are no experiments in this area, but people are thinking about it. There are proposals at JPAC in Japan or at CERN, which are under evaluation. And also, there may be a future in lepton flavor violation physics. For example, also at JPAC, at this proton machine in Japan, you may reach a branching ratio less than 10⁻18. For mu to E conversions in nuclei, and the super B factories should be able to do tau to mu gamma with better than 10⁻9. Okay, so that finishes my tour to the possible future of particle physics. And I hope you have seen that an international well-coordinated particle physics program is ahead of us. The first priority clearly is the exploitation of the energy frontier, but also the neutrino sector will be explored carefully. And smaller programs on flavor physics, non-accelerator experiments, and so on will go on in parallel. And I think you can be optimistic. There is enough work for you to do within the next